All right, so unfortunately, thermodynamics isn't the whole story. Thermodynamics will tell us where the reaction will end, right? So it's kind of the study of where the reaction will end. It's the state functions, right? It just cares about the beginning and the end. But that's not all we care about. We also care about how quickly we're going to get there. For example, just because you know a product is going to be formed, if it takes 1,000 years to form it, that's not going to be very useful to you. And so that's when we get into the study of kinetics. That's how fast a reaction will occur. And so if you're thinking about reaction coordinate diagrams, right, you have G right here, you have reaction right here, and then we have kind of A going into B, and we'll say it's exergonic, right? And so we have a decrease, and so B is going to be favored, right? So that's thermodynamics right there. It tells you which one is lower in energy. Kinetics tells you how you're going to get there. Do you have to go over a big hump, and that way it'll take you a long time? Or do you have to go over a small hump? In that case, it'll take you a much shorter amount of time. And so again, just a bit of review from Gen Chem. If we have something like A plus B going into C, we can write a rate law for this. So rate is going to be equal to K times the concentration of A to some exponent times the concentration of B to some exponent. Remember that these brackets mean concentration. And that these exponents can only be determined experimentally. So for example, we have a reaction coordinate diagram. We start off with A, we end up with B. If we have to go over a big hump versus a little hump. So remember, the point from your reactants to the top of the hump is called the activation energy. It gets E sub A, so there's that activation energy. And then there's that activation energy, right? These are two different pathways you could take. And the bigger your activation energy is, the slower your reaction is, right? So in this purple reaction, this is slow. And in this orange reaction, this is relatively fast. Whereas down here, we have delta G, right? So delta G doesn't tell you how fast the reaction occurs. It just tells you kind of where it's going to end up when it is done. Just some things to keep in mind: when we increase the temperature, we increase the rate of the reaction. And there's that good old rule of thumb that approximately for every 10 degrees Celsius increase, you get 2 times as fast of a reaction. And this is exponential. So for example, 40-degree increase would result in 2 to the 4 times faster, which is 16 times faster, which is quite a bit. This is just a general rule of thumb and not always true. There's also other things that influence the rate of a reaction, such as the orientation factor, which tells you basically, let's do a little example of it. This will play a pretty large role in organic chemistry. So for example, we have AA plus B to form AB plus A, right? And so in this case, A could hit this molecule, or B could hit this A, or this A. Either way, you'll get a reaction. Whereas if you had AC plus B to form AB plus C, in this case, if B hits A, that's a reaction. But if B hits C, that's no reaction. And so in organic chemistry, we're going to take a look at the shape of the molecule to determine, what's its most likely reaction point. And then finally, we have catalysts. So remember that catalysts lower the activation energy and thus make the reaction go faster without being consumed. So they take part in the reaction, but then they regenerate themselves, right? So for example, if we have G here, reaction, maybe our reaction goes from A to B, and this is our normal reaction. and then maybe we add a catalyst, and now our activation energy shrinks. We could also change the mechanism, for example, make it a two-step reaction instead. So just a quick review of kinetics.